settings. Let me just log in. Concerned to see this. I think we are ready to start. So the question here is very simple. You have a transfer function, again, a simple one, first-order transfer function. What is the form of this transfer function? Do you understand the question? Then it's very hard to give an answer. So is it A, normalized, B, non-dimensional, or C, neither? Does this make more sense? When do we say a transfer function is normalized? So A, case A. Sorry? Pulse. A transfer function is normalized when the coefficient multiplying the highest order term of S is 1. So if this is 1 times S, the transfer function is normalized. Okay, so it's A. This transfer function is normalized because first of all, the highest order term is S. It's a first order polynomial. And the coefficient multiplying S is 1. Non-dimensional means that the last term, the term with S to the power of 0 equals to 1. So this transfer function is also non-dimensional. So this is a special case. Numerator is nothing to do with the form of transfer function. The numerator is there because there has to be a numerator. Okay. Guys, in the future, before I answer this, I'm not terribly picky about people being late, but could you use those two doors if you're late, rather than just walk in front of everyone, you know, and very slowly on top of that? Okay, sorry, the question at the back, yeah. Non-dimensional, that the last term, so if you have S to the power n, sorry, A and S to the power n, plus A n minus 1, S to the n minus 1, all the way until A is 0, S to the power of 0. For a normalized AN, so for normalized AN has to be equal to 1. For non-dimensional, A naught has to be equal to 1. The last one, which is this one. So this is a special case that the transfer function is both normalized and non-dimensional. But that's because the coefficients are such that that is possible. In more general case, you will have either normalized or non-dimensional or neither, and that happens when AN is not 1 and AO is also not equal to 1. So case when you have, I don't know, 6 over 3s plus 2. So this would be neither. And this is just to clarify, this is just the denominator. The numerator has no effect on this definition. Okay, any other questions? Okay, the plan for today is to complete lecture 5, and if there is any time left, I will do the past test, or as much of it as the time allows. Lecture 5 first, because lecture 5 is actually all examples, solved step by step in detail. Okay. So lecture 5 is really more examples, and the complexity of the system is now increased. Lecture 4 was all about or most about first-order systems, trying to understand what the meaning of a time constant is, what time constant really represents. Now we are going to move to higher-order systems, mainly second-order systems. Okay, so here we have an electrical circuit. Input is EI, output is EO. We want to find the transfer function of this system. And because of the complexity of the system, I strongly suggest that we write as many differential equations as necessary to fully model the system. So first of all, if current here is I1, here it will be split into I2 and I3. And then we can write an equation, a voltage equation for each of the 3 loops here. So the first equation, and we are also introducing voltage across this capacitor, so that will be E. So we are introducing some intermediate variables that we are going to get rid of later on in the process of modeling. So we are not going to need in our transfer function I1, I2, I3, or E. So all 4 have to be eliminated. We want to end up only with EI and EO, input and output variables, and their derivatives, if any. So derivatives, OK. But all other variables have to disappear eventually. So the first equation describing this loop here, voltage EI will be equal to voltage across the resistor, which is I1, R1, plus voltage E. That's this one. That can be rewritten this way, if necessary. Second loop, voltage across E, voltage E will be equal to the voltage across the resistor, which is I2, R2, and plus voltage across this second capacitor, which is EO. So E equals I2, R2 plus EO. Now, third equation, let's define this current, I2, in terms of the capacitance of this capacitor. So I2 equals C2 times EO dot, the definition of a capacitor. The same for I3. I3 equals C1 E dot. And finally, I1 will be equal to I2 plus I3. Now, this looks like everything we can write about the system has been written. But if you're not sure, have another check. 1, 2, 3, 4, 5 equations. So we have written 5 equations. How many variables? We have 3 voltages, EI, E, and EO, and 3 currents, I1, I2, I3. So that's 6. 6 variables, 2 equations. Okay, it's probably the weather. I mean, it's so humid and the pressure is varying. Okay, so once again, 6 equations, 5 variables. 6 equations, 5 variables. That's exactly what you want. Not 6 and 6. You are not solving simultaneous equations. Your intention is to end up with 1 equation with 2 variables. So you need to have, if you have n equations and n plus 1 variables, you are probably on the right track. If you don't have that, you have to have a closer look at your system. Maybe you haven't written all equations that describe that system, or maybe you have written too many. Maybe if you count this as an additional equation, then obviously that will be wrong. But this equation is exactly the same as this one. So you don't just rewrite an equation in a different form and think, well, that's my additional equation. So you have to write all those equations that are independent from each other. OK, now that we have 5 equations and 6 variables, let's eliminate the intermediate variables, I1, I2, I3, and E. OK. First, if I1 equals I2 plus I3, then let's substitute I2 and I3 with EO and E. Now, E from the first equation, E from the second equation equals I2 R2 plus EO. And instead of, so EO we will keep, but instead of I2, again, we write what we know about I2, which is this equation here. So we are getting C2 R2 EO dot. If we differentiate this, we'll get E dot equals EO dot plus C2 R2 EO double dot. Of course, you realize C and R quantities are all constant. So all resistances, all capacitances, if you can say that, are constant. Then from the first equation, you can write that I1 equals to the difference in voltages divided by R1. And that is equal to what we already written about I1. Okay? So now that we have this equation, we got rid of all currents. Now we have only voltages in this differential equation. So what we are really doing here is manipulating those equations to gradually get rid of those variables we don't want. Okay, so now focus on this part. Okay, EI over R1 minus E over R1 minus, we are bringing some variables to the other side, C2 R2 over R1. Sorry. To explain this a little bit better. E equals to EO minus C2 R2 EO dot. So instead of E, we are writing what we know about E. Here, E is a function of EO, and we are happy with that. So we are now introducing EO here and here. The right-hand side, well, this term doesn't change because it contains EO, something we want to keep. But E dot, again, can be taken from here. So it is C1 times EO dot plus C2R2 EO double dot, second derivative. And this equation is what we wanted to achieve. One differential equation with only input and output voltages, input and output variables. Everything else is gone. That's what we wanted. All that is left is now rearrange everything, bring EO terms to left-hand side, so EO double dot, EO dot, and EO, and EI terms on the other side, on the right-hand side of the equation, which is EI. Maybe you can introduce some simplifications. C1R1, let's call it T1. C2R2, we can call T2. So here we are going to have T1, T2. Here we are going to have T1 plus T2 plus C1, R2. Sorry, R1, C2. So this term we haven't defined. And this represents the transfer function of that particular circuit. Question, yeah? Yeah, you will be given equations of voltage across a resistor, voltage across capacitor, and voltage across an inductive coil. Those three you will be given. Yeah, I guess that's enough. I mean, knowing that current at a node, that sum of all currents will be zero, so currents in minus currents out are zero, I guess that's obvious enough. Yeah. Yes?
So can we do it like nodal analysis or mesh analysis, something like that? Can we do it that way?
Any way that is valid, you know, we are familiar with other ways than only this one. So any way you achieve the, I mean, as long as it is a properly laid out procedure, is acceptable procedure. The other way, I don't think it is terribly applicable to this, but those who attended the classes today, I'm pretty sure the demonstrators did the impedance method as well. But I don't think it helps very much in here. You will have to do pretty much the same thing. The impedance method is also acceptable. Yeah, other questions? I'm just, sorry to completely answer your question. I still believe that you will end up with plenty of equations anyway, and you will have to eliminate them. Yeah. So I don't think you can invent a very, very quick method. Okay. Other question. This example 6 I'm going to skip today because just briefly to explain how it works, how this system works, and then why I'm skipping it. You have a water tank, or tank with some liquid. The flow into the tank is Qi, the flow out is Qo, and then you have a height. So it looks like a water tank system we dealt with last week, but the difference is that this valve, or therefore the flow in, is variable. It is controlled according to how high the level is. So this system is effectively an automatic control system. So if you set what height you want, this system will maintain constant height. Because if for whatever reason the level drops, if you have too much evaporation, as a result, the valve will open more and will allow more flow in, which will bring the height up. Or vice versa, if for whatever reason you have too much height here, then the float will go up, this lever will drop and close the valve a little bit to reduce the flow in. This is an example of automatic control. And that's what we do in lecture 9. And also the analysis will show you something which is, again, which is lecture 10, steady state errors. So this system has inbuilt errors in there. So that's not something that is terribly relevant now, apart from the modeling itself. If you want to practice those equations, you're most welcome, but we'll leave this example when we get to lecture 5 in 2.5 weeks. OK, that's why we are skipping. And I might put it into a test paper as well, so that's another. No, I won't. OK. A thermostatic tank. OK, and here is a description of what it does. So you have a very hot fluid, a steam, no, fluid, which is steam, going through this coil. Now, coil loses heat, so heats the water around it in this particular tank. And tank loses heat into the atmosphere through the walls of the tank. So here you have two thermal processes. One between the coil and water, and the other one between tank, water, and ambient. Two equations. Two processes, two equations. So we are going to write two equations. They say here that Qi is the net rate of heat through the steam. That means it involves the rate of heat that comes in and the rate of heat that gets out, which won't be the same. But the difference between the two is Qi, net rate of heat. So that's how much heat is left, transferred into the water tank. That is our input. So if you consider this coil as your control volume, as we said last time, now you have to see what is the rate of heat that gets into that coil, what is the rate of heat that gets out of the coil. And the difference will be the rate of change of internal heat. Rate of change of internal heat, if temperature inside the coil is Tp, so the rate of change of heat will be C1 Tp dot. Capital C, so you have heat capacitance. And C1 would be equal to small c1 m1 mass. But here we don't really have mass, so let's say with capital C1. So that's the rate of change of heat. That will be equal to heat in, which is Qi, minus heat out, which is the heat that travels from the coil into the water surrounding the coil. That will be some constant. We don't even have to know the name of that constant, the name of that coefficient. But why that heat flows from one medium to another? Because there is a temperature difference. So Tp minus To is what drives that process. And now very similar equation to the other medium, that's the water outside the coil, so water in the tank, receiving heat from the coil and losing heat into the atmosphere. The difference between the two is rate of change of internal heat. Rate of change of internal heat, again, will be some sort of constant. Again, you don't have to know which constant. Some sort of constant times TO dot, rate of change of temperature of water. That is equal to heat in. But heat into the water is the same as heat out of the coil. There is no other way that heat escapes from the coil but to move to water. So these two have to be the same. And the rate of heat that water tank loses into the atmosphere will be, again, some other constant times the temperature difference once again. Temperature of water inside the tank minus temperature outside the tank. TA, ambient temperature. So we have two equations. We have how many variables? We have TP, and we have TO, and we have TA. Okay. Sorry. We have TP is a variable. That's temperature inside the coil. TO is temperature of water. That is variable. And QI is our input. That's three variables. TA, outside temperature, is assumed to be constant, although it's not clearly written here. TA, temperature of the air around the tank, is assumed to be constant, or it is not affected by this thermal process. So although we are losing heat, well, the temperature in Sydney will be still the same. Okay. So three variables, two equations. We can move on. Now, what do you want to eliminate? You are not interested in TP. You want to keep QO as the input, and you want to keep TO as the output. Now, there are different ways of doing this. How you eliminate TP and TP dot between these two equations, this is one of the ways. Okay. Now, if this and this is the same, so we can equate what this term B1 TP minus TO equals to in the first equation and what it is equal to in the second equation, and equate those two terms. So what you're going to have from the first term is QI minus C1 TP dot, but that becomes plus on the other side of the equation, and then you have plus B2 TO minus TA, and then you will have plus C2 TO dot. Okay. Now we still have TP dot that we don't want. So now we will take the second equation, differentiate the second equation, so that will give us TP dot. Everything else will be either the input or the output. TO, TO, TO. TA is a constant, so it will disappear. A differential of constant will be 0. Okay, so now when we differentiate equation 2, here is our differentiated version of that equation. So we have TP dot. TP dot from here will be substituted in here. So TP dot will equal 1 over B times the whole expression on the right-hand side. So QI now becomes equal T1 over B1 times this expression plus C2 TO dot and plus B2 TO minus TA. And then we can rearrange a little bit to have TO dot and the corresponding coefficient to have TO double dot over here, sorry. TO dot and the coefficient multiplying it. Now we have BO times TO, and we have BO times minus TA. At this stage, you wish you could create a transfer function, finding the output over input. Of course, Laplace transform first. But the problem is that you can't because you have this constant TA. So this constant prevents you from forming that relation, that ratio, output over input equals one polynomial over another polynomial. What do we do about that? all I can suggest is assume that TA, not assume, decide that TA is the reference temperature for this particular problem. So you're observing, if you do that, if that's what you decide, that means all other temperatures are observed relative to TA. So how does temperature of the water tank changes relative to TA, relative to the surrounding temperature? So if this is what you are going to call a reference temperature, then you can make it equal to 0. So if TA equals to 0, now you are going to have a much simpler differential equation containing the input on the left-hand side, output, and its derivatives on the right-hand side. No constants, no other no other quantities apart from constants. No other variables. Yeah, okay. Yeah, sorry. Because it would still contain TP. I mean, I'm not saying this is the only way to solve it, but you know, we can't do it because we still have TP and we don't want it. Okay, so the only step now that is left is apply Laplace transform to both left-hand side and right-hand side and obtain the transfer function. In this case, as stated here, this would be a non-dimensional form of the transfer function. Yeah, any questions on this problem? Yes? This is still not Laplace, this is still time domain because you have derivatives. I'll just introduce some constants that are to simplify a little bit. Yes? So this 1 over b, okay, so I'm creating now, after the Laplace transform, I'm having qi over b2. Here I have k1, k2 times s squared, TO of s. k1 plus k2 plus k3 times s times TO. And this is just TO. Then I create qi over TO in the S domain. So in the that's on the left-hand side. On the right-hand side, in the numerator, I'll have 1 over b. In the denominator, k1, k2, s squared because of second, k1 plus k2 plus k3 times s, and plus 1. Okay. Now, question 8, back to mechanical problems. A spring mass damper system, a little bit more complicated. So we have two masses, or two blocks of the same mass. The one on the top is suspended from a ceiling of some sort, from a roof, by one spring and two viscous dampers. The second one is suspended from the top one by one viscous damper and one spring. But also there is another viscous damper beneath the second mass. So you have number of springs and number of dampers here. So now you apply a force Fi, that is your input, and you want to get the relationship or the transfer function relating input Fi and Xo as the output. So in this case, Xi will be our intermediate variable, the one we'll try to eliminate. So what is suggested here is to write a force equation for each mass separately. So treat each mass as a free body, so draw a free body diagram of each mass. So for this one, you eliminate all other components and substitute them with appropriate forces. So here, instead of this force, so obviously when mass moves down, you will have force acting against the motion of the mass. In this damper, the force will be proportional to xo dot, because the other end is not moving. The other end is not moving. Okay? So C times xo dot. This force will be proportional to the displacement of mass, xo, so it's k, stiffness k times xo. Here you have the same as with the first one, apart from the coefficient is different, so it's not the same damper. So now you have d times xo dot. On the other side, you have these two forces pulling down. So this force will be equal to c times relative velocity between this point and this point, which is xo dot and xi dot. So xi dot minus xo dot. I expect a question here. How do we know it's xi minus xo, not xo minus xi? Because someone asked that in one of the tutorial classes when I was there. So you have that question, or you have the answer. Okay. Yeah. Well, first of all, we decided that everything, all forces and all displacements are positive downwards. Okay. So when you apply this force, this is how you initiate the process in this particular system. That's where the process starts. And so pulling force, applying the force down, Fi down, pulling this mass down, means that first mass, this bottom mass, will move down as well. Xi. As a result of this displacement xi, you will have this displacement. So this mass at the bottom is pulling this mass at the top. So first, this is what happens first. Then as a consequence, you have this displacement. That would be my explanation. Now, you are free to say that xi is positive upwards, or xo is positive upwards. But you will make the probability of making a mistake extremely high. It's not necessarily wrong by itself. But then when you start deciding which sign is right and which one is wrong, you are, as I said, increasing the probability. Yeah?
So say the force was initially put up.
Yeah.
Would you assume xo and xi up?
I would do that. I would do exactly that because that's natural. If you assume opposite, it's not wrong, as I said. But just when you start writing equations, you have good chance of getting confused, at least in one of the terms. Okay, so if you agree this is positive, if you agree this is positive and this is positive, then the force here will be proportional to velocity xi dot minus velocity xo dot, proportional to this coefficient c. And the same goes for spring. It's k times xi minus xo. Please ignore this little thing here, because this is the old money, last century thing, when we believed that inertia was a force, and you were able to draw that force. So just pretend it's not there. So inertia would be equal to algebraic sum of all external forces acting on this mass. Okay, or when you write that equation, inertia of that particular mass is mxo double dot. Now, inertia is always in absolute terms. So the acceleration of mass is xo double dot. No differences in 2 or 3 or whatever accelerations. The absolute displacement of the bottom mass is xi. Therefore, inertia is mxi double dot. And that will be equal, these two forces at the bottom will have plus sign, these three forces will have minus sign. When you rewrite everything, you will get this equation describing the mass on the top, the bigger one. I mean, bigger by volume, masses are the same. Now you repeat the same for the bottom mass. So you have force Fi pulling down. All other three will resist that displacement. As mass moves down, this damper will resist. That's obvious. But again, think about the beginning of the process. As this mass moves down, this will create a resistance. Okay, the spring will expand initially, therefore pulling upwards. And similar will happen with the damper. Okay. So you have this force acting upwards, this force acting upwards. Fi, as we said earlier, acting downwards, but this one acting upwards as well. Yes? Yeah, that's why I'm asking you to ignore this, ignore this. It's not acceleration, that's inertia. But inertia, at least now we decided inertia is not a force you can show. Inertia is just the sum of existing forces. So I thought, when I was rewriting these notes, I thought I got rid of these, and I didn't. Or either put the old drawings back into the file, or just forgot to remove that. Because I know every year I have questions on this. So whatever you see here, this MXO double dot, pretend it's not there. And this one, pretend it's not there. So inertia will be equal to the algebraic sum of all forces that act, external forces that act on the particular mass. Okay? So this will be the equation describing the second mass. So now we have two equations. How many variables? 3. Fi, xi, xo. That's what we want. Now we can play with these two equations. Now the problem is you want to eliminate xi. But in those two equations, you have xi, you have xi dot, you have xi double dot. So eliminating all three could be a tedious process. To make it simpler, what I suggest is before you eliminate the intermediate variable, apply the Laplace transform to equation 1 and Laplace transform to equation 2. So that way, you get two new equations in the S domain. Okay, two equations with three variables, Fi, Xi, Xo. And now, what is good about this is that Xi has no derivatives, only Xi. So it is now much easier to eliminate Xi between the two equations. Again, to keep the process simpler, we can rewrite equations as F1 XO equals F2 XI. Over here, you have F3 XI equals Fi plus F2. If you notice, this is the same as this. F2 XO. And now, once again, you want to get rid of Xi. So eliminate Xi between these two. Okay? You think it's too much of a jump from this point to this point. Okay. Xi will be equal to F1 over F2 times XO. Write it here. Sorry, where is it? Write it here. So you have F3 times F1 divided by F2. F3 times F1 divided by F2. Okay? And then Fi and XO remain unchanged. So you end up with one equation with Fo and, sorry, with Fi and Xo only. Okay? So you can get, this would be the transfer function. Now substitute back the expressions for F3, F1, and F2, and you get quite a lengthy denominator down here, but that would be your transfer function. What is the order of this transfer function? The order of a transfer function is equal to the order of the polynomial in the denominator. Here you have s squared multiplying s squared, so the highest term will be s to the power of 4. So this will be a fourth order polynomial and therefore the fourth order transfer function. How many time constants, at least in theory, are we going to have? 4. The order of the polynomial in the denominator determines the number of time constants, at least in theory. Back here, this transfer function is of the second order, therefore 2 time constants. How many steady-state gains does this transfer function have? 1. And the value is, guys, you're either too shy or you are falling behind. It's 1 over B2. That is the steady-state gain. Ignore this one, as we said. Where is the transfer function? OK, what is the order of the transfer function? Well, I can't believe. OK, it's 2. So I said you are too shy. Maybe you just don't want to talk to me. That's OK. I'm here to talk. So it is second order transfer function. That means 2 time constants, in theory at least. But if we can factorize this polynomial, then definitely we'll have 2 time constants. And the steady-state gain will be 1. How do we know? Well, first of all, this is a non-dimensional form of the transfer function. That means steady-state gain, or DC gain, can be read right from the numerator, which is 1. OK. Let's see if we can finish. OK. Example 9. At least we can start, and then we finish after break. So you have a long shaft. Okay. And along that shaft, you have few places where we are interested in angular displacement. So the input angular displacement is θ1. Here you have torsional spring. So that means that angular displacement of this point will not be the same as θ1. So it will be something else, θ2. Here you have viscous damper, but this time it is rotational viscous damper. On the other side of the viscous damper, angular displacement θ3. Another spring, different stiffness K2. Let's call this θO. Here you have a disk. Disk has its own inertia. But because the disk itself is rigid, it is the same displacement on the other side of the disk as well, θO. And finally, you have a viscous damper and another viscous damper, but the cylinder of the viscous damper is fixed. It does not rotate, only this piston inside, if you want to call it piston. So you have 1, 2, 3, 4 variables, θ1, θ2, θ3, and θO. We would like to be able to write 3 equations, since we have 4 variables. So the equation, let's write an equation describing this first spring here, stiffness K1. So the torque across the spring equals to stiffness times relative displacement of 2 ends of the spring. Very similar to linear motion when you have a spring equal k x1 times x1 minus x2. Just here you have θ1 minus θ2. So relative angular displacement instead of a relative linear displacements as we had earlier. That torque is the same as the torque across this viscous damper. And that will be equal to C1 times relative angular velocities, θ2 dot minus θ3 dot, relative angular velocities. That will be one equation. The other equation you can write is that the torque in the viscous damper equals to torque in this spring. So this is your second equation. The same logic applies. Now, the torque in the second spring minus the torque due to the friction will be equal to inertia term. This term is the rotational motion. So J times theta O double dot, angular acceleration. Because if you take the disk only, the inertia of the disk will be equal to positive torque minus negative torque. Take again this big disk as a free body, and then you have one torque acting in one direction, the other one opposing the motion. So torque due to the spring creating the motion, the torque in the viscous damper opposing the motion. The difference between the two will be the inertia term. But what is important is that you have three equations. 1, 2, and 3. So 3 equal signs will give you 3 equations. So you can apply the same method as we did so far, eliminate the variables you don't want. Theta O and theta 2 and theta 3. Theta 1, you keep it as the input. Theta O, you keep it as the output. Or what we are describing here, you can create a slightly different model of this system that will maintain the presence of all variables, theta 2 and theta 3 as well as theta 1 and theta O. That is something you're going to need later in this course, this method, once Dr. Kwok starts teaching his part. Yeah, this will be called state space, but at least I should show you because potentially this is a very simple, this method can make your work simpler if you know how to apply it. Okay, but we'll leave it for after the break. Okay. Any questions? Okay, let's have a break now.
Question here. If this is equal to this,
Yes.
equal to 0, right?
Well,
There's no J.
there is no inertia, so the entire torque acting in the spring is transferred to the damper.
So it's not 0, it's just transfer.
Yeah, they're just equal to each other. It's not zero.
So it's basically the force is equal to
No, they're not forces, just torque.
so
Yeah, because it's all rotation. So ignore force.
why would it be equal?
Okay. So it is in a way similar to.
Is it supposed to be a minus? Because you said they subtract each other.
If you do forces, it will be equal to 0, right? There is torques. That's why it's different.
It is in a way similar to. Yeah. These ones.
Yeah,
Apart from this is linear and the other one is
but
rotation.
here there is no mass, so it will be 0.
No. The force is constant across this system because there is no mass. So the force in this spring equals to force in this spring. The force in this damper equals to the force in this spring. But here they are not constant because there is mass and there is inertia. So this force and this force are not the same. So back to where are we? Here. Therefore, this torque and this torque are not the same. This torque in the spring equals to the torque in the spring, in the damper, the same as this force and this force are the same. So the torques are the same. They're not zero, they're just the same.
Oh, so as soon
So,
as there's mass,
or let me put it this way. You actually apply the torque here, and you just don't want that variable. That's not what interests us in this problem. But that torque equals to K times theta 1 minus theta 2, which is the same as this torque, which is the same as this torque, which is not the same as this torque because here you have inertia. Once you have inertia, the force or the torque are not going to be the same. So this inertia term will be equal to this torque minus this torque. So if you ignore the rest, this inertia term equals this minus this and this goes away.
what's this term?
That's due to this damper.
Aren't they supposed to subtract each other?
No. This and this subtract each other to be equal to inertia. So this and this, they are external torques. One positive, one negative.
Yeah, and also,
Okay.
another question is, here, you know how the area is expanded if you put water into it?
Yeah.
Yeah. So, but then how come if you put a coil into the water, the area isn't expanded?
Yeah, it is a constant. So I said that B1 or whatever B2 or whatever we said, that's a constant that includes all possible constants.
Okay.
Okay. So for this problem, we didn't want to put too many constants. We just say the process is proportional to temperature.
Okay, so it's basically like HA.
Exactly.
Thank you.
Just explain that. Explain that. Because the process starts with the force. I mean, there are a number of ways to explain it. I would say the process starts with the force. Okay. So the first thing that happens after you apply the force is that xi. As a result of xi, xo. So the force equals to xi minus xo. The force that goes down. The same. It still yes, why not? So if you analyze this mass, the mass is moving down, this force is pulling this mass up. But it is also moving, those two forces, when you analyze here, this mass, the movement of this mass is opposed by these two forces. But the movement of this mass is actually generated by these two forces. When you think of this mass only, why does it move? Because these two forces are acting down. Probably. Yeah. Yeah. Apart from, I didn't study 2300. I studied under different.
So just like this
Yeah.
one.
Yeah. So it's a.
The formula mx dot
Yeah.
plus
Yeah.
cx dot.
Yeah. So it is a free body diagram, and you just need to see what components are generating these forces. Is it a spring? Is it a damper? Okay.
I can't understand.
Well, you see, the whole thing in brackets, we call it F1.
Yeah.
This thing in brackets, we call it F2.
Oh, so this one is F2
Yes,
and this one
is F1. Yeah.
So
This one is F3 because there is a slight difference. So this one is F3,
this is F3.
but this one is still the same as this one. So this is F2 again.
Okay, so this is F3.
Yeah.
Oh yeah.
Okay. I think I'll have to repeat that because the guy before just asked the question again. Yeah.
Yeah.
Okay. So just what we don't show here, there is a torque applied. That's why you have all these rotation. But that torque equals to the torque across the spring, K1, theta 1 minus theta 2. That torque is the same as torque across the damper, which is the same as the torque across this spring. But over here, this torque is not the same as torque over here, because you have inertia here. Instead, what you can write that inertia, so J theta O double dot, equals to this torque minus this torque. Yes, this torque is theta P minus theta O times K2 obviously, minus C2 theta O dot. That equals to inertia. And that is really similar to these problems here. Here you have a constant force. Constant force. Here you don't have a constant force. This force here is not the same as the force here because of inertia.
Thank you.
I think I'll have to repeat that.
Yeah, one more thing.
Yeah.
About this stuff.
Oh, that's,
This one.
Yes.
This one. Yeah. For the x double dot, so it's not acceleration or it's acceleration.
no, it shouldn't be there. I ask you ignore that. Ignore this arrow, and ignore this arrow here.
But how about for the x double dot, so what
So
is that?
inertia, if you remember, inertia is sigma of all forces.
Yeah, I know.
So inertia equals this plus this minus this minus this minus this. And this is inertia. When
so
I was a student, inertia was a force. and it will be always acting opposite from where the acceleration is going. You don't teach it, no, you are not taught that way, so this should be removed.
So this stops is a inertia, it's not an acceleration.
No, acceleration is going down. That's inertia, but just try to remove it
It's
from your...
also same as this one, right?
Yeah,
This one.
yeah, that's right.
This one here. So let's see that double dot here.
Yeah. No. Ignore it from the drawing. I only said ignore it from the drawing. Just pretend it's not written, drawn. Pretend it's not drawn, but it does exist. It's inertia equals to sum of all forces. This inertia is equal to the sum of all forces.
So we can always assume both directions, like in any way. Like, so you mean I should ignore the sign of this one, right?
Yeah,
so
ignore.
like I can assume that it's going down or it's going up.
No. Just say mxl double dot equals to the sigma all forces. This force, sorry, this plus this, minus this, minus this, minus this.
Also, like the sum of these two is maybe smaller than these two.
We don't know. We don't know.
No, I mean like when calculation, the sum of these two is smaller than that three.
Yeah.
So the sign will be positive.
Yeah.
So in other ways, negative.
Yeah. Another quick one, yeah.
Yeah, so all this, will the transfer function be increased because your input is equal to 1?
No, this is the output for given conditions. This input and these initial conditions, this is the output.
Yeah, but then the output is equal to input times.
No, that you can use that only when you have zero initial conditions.
Okay.
So the transfer function is ignore initial conditions and ignore the form of the input. So it is just any generic R of t. So then apply Laplace on the left, Laplace on the right. Find output of C over R, and you'll get 1 over S squared plus CS plus 10. Just one. That will be the transfer function. Okay. Yeah, quick one.
Very quick question. I don't understand what this means, DC.
DC gain or steady state gain. Okay. You get it because on previous stage we have a definition. When you write your transfer function in a non-dimensional form, so instead of k you have 1, that means here you have m over k, but that's irrelevant. Here you have 1 over k. 1 over k is the DC gain. This is steady state gain. No, I guess we can move on. Now, I had many questions during the break, but one is, repeated most of the time, so I'll try to address that. Obviously, I didn't explain it well enough. Now, this shaft rotates. That means that somewhere here, a torque is applied. So someone applies a torque. As a result, you get this angular displacement, and this angular displacement, and this, and this, and this. So it is due to a torque being applied. This situation is similar to these systems here that you've already seen. Apart from here, you have linear displacements. You have force instead of a torque, and then you have linear displacements instead of angular displacements. So in this case, force is constant throughout this system. So the force in this spring equals to force in this spring. Over here, the force is constant again. So the force through this damper is the same as the force through this spring. Here, the force is not constant because you have inertia, and you have inertia. So the force acting here is not the same as the force acting underneath. The difference between those two forces equals to mx double dot, m1 x double dot. So in this case, those two forces are not the same. So if the mass is negligible, if you can ignore the mass of the spring, the mass of the damper, you have a constant force. You have a constant force. Back here, you have a constant torque until you reach this disk whose inertia is not negligible. So the torque in the spring, which is K1 times relative displacement, theta 1 minus theta 2, is the same as the torque in the damper, which is equal to C1 times relative velocity, angular velocity, theta 2 dot minus theta 3 dot, which is the same as torque in this spring, which is K2 times relative displacement. But then when you reach this disk here with the significant inertia, then what you can do is write a free body diagram. So you have the force from the spring trying to turn this disk, and the force in that damper resisting that rotation. The difference between the two equals to inertia term. So inertia term, J theta O double dot, equals to torque in the spring minus the torque in the damper. Therefore, this plus here. And this torque in the damper is moved to the right-hand side of the equation. Okay. I hope this makes it a little bit clearer before we move on, because what I'm going to do here is not eliminate theta 2 and theta 3. I want to keep them within my mathematical model. And for this, I will need to know something about matrices. Okay. So I want to write all three equations. So I said this equal sign defines one equation. This equal sign is the second, and this one is the third equation. So I want to have theta 2, theta 3, and theta O on terms on the left-hand side, and theta 1, because that is my input, I want to keep it on the right-hand side. So from the first equation, I have K1 theta 1. That means K1 times minus theta 2 will become plus when it moves to the other side. So I will have K1 theta 2. C1 theta 2 dot will be positive, and if I apply Laplace transform, this dot will turn into an S. So we'll have C1s times theta 2. But in this first equation, I still have this expression here, minus C1 theta 3 dot, and that's why I have S. In this equation, there is no theta O, so I have nothing here. Now, second equation, repeat the same process, but this time I don't have theta 1, so I will have 0 on this side. Everything is on the left-hand side. So I have C1, okay, so if this is, okay, now I need to bring, for the second equation, I'm bringing this term to the right-hand side. So I get minus C1 theta 2 dot, so therefore C1s. And I have K2. Yeah, that's true. So with theta 3, I'm going to have C1 times S because of the dot here, C1s. And I'm going to have K2 times theta 3, K2 times theta 3. And now, for the first time, I have theta O, the negative sign, times K2, minus K2 theta O. Now I repeat the same process for the third equation. So I don't have theta 2 here, so I have 0. I don't have theta 1, so I have 0. All I have is theta 3, and it appears here. And I have theta O, which appears 3 times, here, here, and here. So I have this expression here. Now I can rewrite these three equations in a matrix form. If I introduce the vector, theta vector, theta bar, which has 3 components, theta 2, theta 3, and theta O, then I can rewrite the whole 3 equations as a matrix equation, where A times theta bar becomes equal to the vector with these 3 components, K1 theta 1, 0, and 0. Okay. What are the terms in the matrix? This will be A11, this will be A12, this 0 will be A13. Then A21, A22, A23, A31, A32, A33. So get a 3 by 3 matrix. That's what A is. Then you can express theta bar, the output vector, in terms of everything else, which is a to the minus 1 times this vector here, k1 theta 1, 0, 0. Okay? What is a to the minus 1 or inverse matrix? By definition, it is equal to adjoint matrix divided by the determinant of A. Okay? Or you have a slightly quicker way of solving that, because adjoint matrix is a bit tricky. Not tricky, it's tedious. You have to find the cofactor. It's actually a matrix of cofactors, so you need to find cofactors. You all know that, right? Okay, I think I do, so I think you do as well, but it's been a while since I used that. Okay. Or you can use a shortcut using so-called Cramer's rule. Cramer's rule will help you. Yeah, you know Cramer's rule, or you don't. Doesn't matter. At least for my part of the course, you don't need to play with matrices and vectors at all. You don't have to use this. But it's my duty to prepare you for Module B, for the second half of this semester. So with the Cramer's rule, you can extract any of these components from the theta vector, okay, and get it in terms of, yeah, we call it theta I. So is it theta 2, theta 3, or theta O? Okay, so for example, if you want to express theta O in terms of theta 1, this is how you do it. You use this Cramer's rule based on the matrices you had earlier. Okay, and you get a nice little expression here, a third order transfer function. Okay, this you should get, so theta O over theta 1, output over input, and you get this numerator and this as a denominator of the transfer function. So this would have been possible had you applied the methods we used earlier. Try to go step by step, eliminate theta 2 and theta 3 from these three equations, because this is effectively three equations with 4 variables. So it is possible. You don't have to do it this way. You can do it the old-fashioned way, or eliminating unwanted variables, intermediate variables. Any questions? No, just stretching. Any other questions? No. And the final example for today, and this is where we finish lecture 5. This is where we finish potential questions for the test on Thursday. So this is called a servo mechanism. So just to explain, those who don't know how servo mechanisms work, just a brief explanation. Here you have a hydraulic fluid coming under high pressure. This part here is called servo valve. And this servo valve features this double spool piston that can move left or right. So it has 1 degree of freedom. It can only translate left or right. As it moves, say, to the left, then this orifice, this canal, will be open to the flow of this high-pressure fluid. So it flows in here and creates a high pressure compared with low pressure you have on the other side. That pressure difference will create a force that will push this ram to the right. Or opposite will happen. If you push this piston to the right, then you will open this orifice. High pressure fluid will enter on this side, push the piston to the left. In that case, this ram moves to the left. So this will be an example of a hydraulic servo mechanism. Pneumatic servo mechanisms work the same way, apart from with the pneumatic, you have to take into account the compressibility of the fluid because it's air. But here, if you assume it is a hydraulic, now we assume, we already told it's a hydraulic system, no compressibility, so equations are simpler. Okay, this is where the process is controlled. So it's a human operator that moves this lever to the left. As a result, because the pivoting point is here, the lever will move, the whole lever will move to the left, therefore this point as well. As you move this point to the left, that's how you move this piston. That's how you allow high-pressure fluid down into the actuator, into the cylinder. So first, let's write the equation describing this particular lever here. And here it is. So using the similar triangle rule, D1 and D2 are variables, so D1 divided by R1 plus R2 will be equal to D2 divided by R2. Therefore, this equation here, let's call it equation 1. Here, as D2 applies, so as the piston moves, doesn't mean that it moves completely to fully open this orifice. So it may only partially open the orifice. So you have flow through the canal will be proportional to the, where are we? Down here. Which the flow through the valve will be proportional to the displacement D2. The more you move, the more you open that orifice, so you allow more fluid through it. And we assume this relationship is linear. In practice, it's not so true, but at least this is a linear kind of subject. And finally, why is this piston moving? Because there is a flow getting into one of the chambers, into one of the sides. So flow Q, assuming no leakage or anything like that, will be equal to A times D3 dot. Area A times the velocity of the piston. Because the volume flow, Q is volume flow. The volume flow that gets in gets translated into change of volume. Change of volume A is constant, so you have D3 dot. Now, we want to relate D1 to D3. D1 being the input, D3 is the displacement. Right. So, 3 equations, 1, 2, 3, 4 variables. D1, D2, D3, and Q. Keep D1 and D3. Everything in the middle needs to disappear. Eliminating 2 equations between these 2 variables between these 3 equations should be easy. So A D3 dot equals to Q. Q equals K2 dt, D2 rather, and D2 equals D1 times this constant here. So it's actually not terribly difficult. Once again, A D3 dot equals Q, which is equal to D2 dot, K D2, which is equal to K D1 R1 over R2. So we have a direct relationship between D3 dot, in this case, and D1. Now apply the Laplace transform. Okay, so this is the equation. When you eliminate Q and D2 between the 3 equations, this is the differential equation. This is the differential equation that describes our system. This is the mathematical model in the time domain. Now you know the rest. Laplace transform of the left-hand side equals the Laplace transform of the right-hand side. Over here, it's S times D3. Over here, everything is a constant, times D1. So D3 in the S domain, D3 over D1, is now equal to K R2 over A R1 plus R2, and you have S here due to the dot over here. We can rewrite this as K1 over S. And we say here, so this is an integrator. Why is this an integrator? Because 1 over S means integration. S means differentiation, 1 over S means integration. Remember Laplace transform. There's just a scaling factor K1, but it is still an integrator. Now, what that practically means that this system integrates whatever the operator or our bulldozer does with the control stick or column, how you want to call it. Our system integrates. So the result will be an integral of the input times K1. Okay, so let's see what that means. If you apply an impulse, so you push the lever and pull it back very quickly, that is a description of an impulse. What is going to be the output? Output equals transfer function times input, which is 1. Okay, Okay, S is missing here. S is missing here. Apology for this. So transfer function K2 R2 over A R1 plus R2 times S. S from here should still be here, down here, rather, here. Okay, times input, but input is an impulse. We assumed a unit impulse for simplicity. The output now becomes a constant times u of t, obviously, a step function. So it becomes a step function. So when you integrate an impulse, you get a step. Step is an integral of an impulse. So if you apply that particular impulse as I described, push the control stick, pull it back to neutral, the output, your RAM, is going to do this. It will be at 0, jump to a constant value, and remain constant. So it is not coming back. So all you'll push the stick and pull it back, the RAM doesn't come back. It stays deflected, this RAM. Moves to new constant position and stays there. Let's now consider a slightly different input. We call it a couple. So when you have a step input followed by a negative step input of the same size, just a few seconds later. So not immediately, like an impulse. So you have two steps, one positive, one negative. This is known as a couple. And the time between those two steps, between the positive and the negative step, is capital T. So again, output will be equal to the transfer function. This time S is here. Good to see. Times input in the S domain, Laplace transform of the input. How do we describe this input? I hope we know how to do it. First, you have positive step, again, assuming unit step, so it is 1 over S, followed by a negative step, minus 1 over S, but this negative step is delayed by capital T seconds. And that delay, that shift, is represented with this exponential term. Okay. Now, the whole thing here, sorry, without S, the whole thing is constant. So that part will not change. But we still need inverse Laplace of 1 over S times 1 over S. That will give us 1 over S squared. Here you have minus 1 over S and 1 over S over here. And you have this exponential term. Laplace transform of 1 over S squared, if you are still not sure, check the tables. It will be a ramped function. So it's T. Inverse Laplace of this second term is also a ramp function delayed by capital T seconds. Okay, so ramp function plus another ramp delayed by capital T. If you try to plot this, first you have the ramp growing from 0 to 10 seconds, to T seconds. After this, this negative ramp will offset the growth, so it will stay constant. So in this case, your RAM is not going to just jump to a new value. It is going to gradually reach the new value and then stay there. Okay. So effectively, in this case, if you want to return your cylinder back into neutral position, first you push forward and back to neutral. Then it stops moving. But to come back to neutral, you have to pull the stick back and again forward. And I don't know if anyone has any experience in driving bulldozers or any excavation machinery, that's how it works. Okay, any questions? hope everything is clear, or you're just waiting for me to start working on this particular problem. Now, I don't have, one of you guys somewhere in the tutorial classes asked me for solutions. I said, please don't ask for solutions. I said, please. So you're still asking. But the reason I'm not giving you solutions is because I don't have them. I really have to sit down and solve the problems again. So that's what I'm going to do now. Maybe there are solutions in the pile of my old papers. So I'm going to sit down and solve as much as I can out of the last year's test. You will have a unique opportunity to see how your lecturer struggles with the problem he created. And I think the best thing to do is actually to split those two screens. So you have the problem and you have the camera. You have the solution here. Okay. Okay, so I'm pretty sure you all read the text. We don't have to spend too much time reading again. We all know if you drop a crate from a plane, first it will accelerate towards the Earth. Then when the parachute opens, it will decelerate. It will slow down. And we don't care about that transient process, how long it takes. But eventually, there will be a point in time when it starts descending at a constant speed. That's what we said here. And that happens when two forces are in equilibrium. One is the weight of the crate. The other one is the resistance of air, D. And we gave you the expression for weight. In case you don't know, it's mg. And the air resistance will be this expression here. So D equals 1/2 rho air times V squared ACD. Everything is constant here. Apart from, we will see what. Okay, where mass is the total mass of the system, G is gravity constant, rho air is density of the surrounding air, V is the velocity, A is the total horizontal cross-section area, CD is the coefficient of air resistance. Question A, if the two forces are in equilibrium, express V in terms of all other parameters. I don't know how much this was worth. If this was 1 mark, this was probably the easiest 1 mark you could get. But there will be very easy parts, and there will be parts that are not easy at all in your test. So easy parts, I really want to see if two people are going to fail, I still want to see who deserves 0, who deserves 1. Who knows at least something. I also want to see if two people are brilliant, but one deserves 10, one 9. I want to make that difference as well. So that's why some parts will be really hard. Good news for the rest of you, the parts that are really hard are usually not worth very much. Most of the questions will be somewhere in the middle, somewhere between very easy and very hard. That's what the most, about 8 marks will be on those things. Okay, part A. So question 1, part A. If mg equals to, can you see this? If mg equals to 1/2 rho air V squared ACD, V will be equal to square root of 2mg over rho air ACD. Is this correct? Yeah. So that was part A. Okay, now B, part B. When the crate is dropped from a high altitude, the air density increases as the crate descends. So we all know that about the atmosphere, that the density around the sea level is higher than density at high altitudes. Okay, so density is a variable in this case, rho air. So now we need to linearize V in terms of rho, assuming everything else is constant. So let's see how we do it. It is a single variable problem, single independent variable. So velocity, linearized if you want this subscript, will be equal to velocity at the operating point plus rho air minus rho air naught dv by d rho air. Okay. Okay. What is the operating point? Operating point rho naught, which is the sea level. Sea level density. So it is a constant. We are not given a value, but we know rho naught is a constant. So we are linearizing about rho naught. So rho naught is the operating point. VL is, everything is constant. Rho air at the operating point is just rho naught. So it is a square root 2 mg over rho naught A, C, D. Now plus rho air as a variable minus rho naught. Here we need this derivative. I'll just change the color quickly. So dv by d rho air will be equal to, now we have everything constant, so I'll keep this constant intact, 2 mg over A, C, D, times square root of 1 over rho air is rho air to the power of minus 1/2. You don't look convinced. So this is equal to square root of 2 mg over A, C, D times rho air to the power of minus 1/2. Square root is 1/2, but this is in the denominator, so it is minus 1/2. Okay. So all I need is a derivative of this part. So it is times minus 1/2 rho air to the power of minus 3/2. Minus 3/2. But I want derivative at the operating point. So this will be rho naught. Okay, so down back here, so it is times square root 2 mg over A, C, D times rho naught to the power of minus 3 by 2. Yeah, now, you're most welcome to stop here, because this is the answer. Or you can decide to rearrange if you wish, if you want to get some points on aesthetics. Good luck with that. Sorry? I left this negative. Negative. No, this is times. Oh, negative half. Oh, thank you. Minus 1/2. Negative half. Okay, good. Yeah, thanks. This is linearized, so I probably lost half a mark for this, not more than that. 0.2. Okay, just to check, this is now serious. So VL, if velocity is linearized, what you have on the right-hand side has to be a linear function. So let's check that. Everything here is constant, no problem. Rho air is the variable, but it's to the power of 1, so this is a linear relationship. This is a constant. Everything here is a constant too. So now we are satisfied. We have linearized velocity. We have answered the question. Okay. And this half, if you miss this half, it's not really a big penalty. There's not going to be a big penalty. But if you end up having rho air squared or anything like that, and you say, I have linearized that, no, you haven't. It's not linear, you have a square. Or if you end up having a square root, or logarithm, or sine, or whatever, this is not a linear function. Okay. Or if you multiply rho air by another rho air somewhere here, if you forget that this is a constant, it is not a linear expression. Okay, part C, actually I'm not going to write. There is nothing to derive. The question is, apart from the usual linearization error, what will be the greatest source of inaccuracy introduced with this approach? Comment in up to 50 words. So if we ask you to comment on something, we really don't want 3 pages of code. If you need 3 pages, you must be wrong. You know, if you tell you 50 words or 30 words, that means, you know, get to the point, explain, and move to question 2. And if you really feel you need more than that, you're not really counting words. 55, no one cares. You know, but you know, just think about that. If you don't think you can explain 50 words, your thinking is wrong. Rethink the question. Now, what is the, you know, whenever you linearize a function, you are going to have, apart from at the very operating point, everywhere else you are going to have a certain linearization error. We are not asking that. We said apart from the linearization error, what is the other biggest source of error in this particular approach, the way we linearize this? Any ideas, or should I quickly answer it? So when you are choosing an operating point, you should choose it somewhere where the system operates. So if you know the operating range, that the system normally works between x1 and x2, then the operating point should be somewhere in between those two, ideally in the middle, but somewhere in between. So then your linearization is as valid as possible. The linearization error is as small as possible. But if this is the operating point, it is really wrong to select operating point. If this is the operating range, rather, if this is the operating range, operating point shouldn't be outside the operating range. Operating point should be within the operating range. Because when you draw a tangent here, your linearization error would be huge. So your linearization cannot be used as a substitution for the nonlinear expression, because this tangent does not describe your system. This tangent does. With a certain small error, it does. So the selection of the operating point is an important thing. It should be within the operating range. In your case, the operating point is the standard sea level density. So we didn't say anything where you are dropping your crate, to which altitude. But in the worst case scenario, it is if you are dropping on the beach, okay? Then the operating point is at the very edge of the operating range, which again is much less accurate than having the operating point somewhere in the middle. So the choice of the operating point here is wrong. Now, of course, there are few places on Earth where the terrain is below sea level. So if that's the case, then your linearization might be correct. If you're dropping from above sea level, but your crate is landing below sea level, but you have maybe 3 cases like that, 3 I'm aware of. Yeah, one is Lake Eyre here in Australia, in Central Australia. But again, that depends on the level of the lake. Sometimes it is above sea level, sometimes below. and you have parts around the Dead Sea in between Israel and Jordan. You have parts of the Netherlands in Europe. That's all I know about. So if that's what you mean, then write it. It will be correct answer. So there are no errors because I'm dropping my crate to, to Holland or somewhere. Okay, that's question 1. Any comments? Yes. It changes because the density changes. So it is in equilibrium at that particular moment. Now it keeps dropping, it keeps descending, and then it encounters more density. So therefore, it is not constant. So we say initially the velocity, so after acceleration, then parachute deploys deceleration. So after that short transient process, we have at some point, we have constant velocity. We write these equations, but over a long period of time, velocity will change because of more resistance. Okay, if you're okay with that. So this was what? 4 marks. So I guess A and C would be 1 mark each, part B would be 2 marks. So for successful linearization, 2 marks already. You passed this question. Question 2, it's only 1 mark, but it's actually testing you how you handle Laplace transforms. So you have a function f of s, so question 2. F of s equals to minus 1 over s plus 1 over s squared and minus e to the minus s over s squared. Part A, find initial and final values of f of t. A longer way is to find f of t, find inverse Laplace transform of f of s. Find f of t, then make time equal to infinity, that will be final value. Make time equal to 0, that will be initial value. A quicker way is to use initial and final value theorems. Here is the final value theorem. Here is the initial value theorem. So you don't need f of t. If you have f of s, you can find the initial value, you can find the final value without having to perform inverse Laplace transformation. So just use these 2 expressions. So initial value first, f of 0 equals to limit when s approaches infinity of what? S f of s. Limit s approaching infinity. S times this function will give me minus 1 plus 1 over s minus e to the minus s over s. Minus 1 will remain minus 1, because when s approaches infinity, minus 1 is not affected. When s approaches infinity, 1 over infinity is 0, so I have plus 0. And the tricky part here, to be careful, s approaching infinity, so the denominator is infinity, but when s approaches infinity, this one is 0. E to the minus infinity is 0. Okay? 0 over infinity is definitely going to be equal to 0. So initial value is minus 1. Final value limit now s approaching 0 of s f of s, which is limit s approaching 0 of the same thing. Minus 1 plus 1 over s minus e to the minus s over s. That equals to minus 1. But here we have a problem. 1 over s, when s is 0, is plus infinity. Minus, when s is 0, e to the power of 0 is 1. Over, when s is 0, we have minus 1 plus infinity minus infinity. Now, this is not minus 1, as we wish, because plus infinity and minus infinity are not necessarily the same. So you can't just cancel them. So you have to go back and say, OK, minus 1 is fine. Is equal to minus 1 plus limit s approaching 0. And I'm going to apply so-called L'Hopital's rule. I'm going to do it. No matter what you say, that's what I'm going to do. 1 minus e to the minus s, which is equal to minus 1 plus limit s approaching 0 of the derivative of the numerator over the derivative of the denominator. That's the L'Hopital's rule. Derivative of 1 is 0. Here we have minus. Derivative of e to the minus s, because of the minus I'm going to get plus e to the minus s. Derivative of s is 1. Now, this is equal to minus 1 plus, when s is 0, e to the minus 0 is 1. 1 over 1 is 1. So the final value is 0. Okay? B, happy with this. Part B, find the analytical form of f of t. Now you have no choice. You have to apply inverse Laplace transform. So f of t, which is inverse Laplace of f of s, will be equal to inverse Laplace of minus 1 on s is minus u of t. Plus, you can't see, but then you can't see the top neither, the top of the page. Okay. So Laplace of minus 1 over s is minus u of t. Plus 1 over s squared is a ramp function, so it's plus t. As I said, this is optional. I have to write times u of t. And Laplace transform of this minus e exponential times something. That indicates a shift in the time domain. So exponential term in the s domain means shift in the time domain. How long is the shift? 1 second. Whatever multiplies s up here, which is 1. So the shift is 1 second. So you have a ramp, negative ramp, shifted by 1 second. So it's minus t minus 1 times u of t minus 1. So this is the first term, this is the second term, this is the third term. And then sketch its graph, so sketch the graph of f of t, indicating clearly all relevant values. So it is f of t. So I'm going to have the first one is actually a negative step 1. So this is minus 1. The second one is a positive ramp, magnitude 1, so it's 45 degrees. And the third one is that after 1 second, we have a negative ramp, gradient minus 1. So minus, can you see this? Okay. So when I want to join these three, I'm pretty sure it's going to be 0 until time is 0. Then here I have this sudden jump down to minus 1. Then I will have a 45-degree gradient up to this point.